So in this video, we are going to study how to use the fuzzer that is provided in the skeleton code of the compiler. So let's say that you implemented the homework 1. So this is not implemented in this this video, but let's assume that you implemented it. Now, suppose that you succeeded in the test. In this video, this file is not succeeding in this test, but let's assume that it succeeded in this test examples, right? C. So now you're about to finish your homework 1, but you have to do one more thing to do. That is fuzzing. You're executing the fuzzer. That is some script that is fuzzing your homework, and this is the argument for your homework 1. P is the shorthand notation for print. Okay, at the first iteration, it found a buggy case, which is this test case 0. And let's see what's that. The test case is residing here, test published here. This is a very long file, blah, 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 blah. And this is about 4,000 lines of code. It is nearly impossible to debug this file on your own. So we provided a script that is reducing the buggy input for your program. So it is doing something, and at last it is going to say, it is going to write something in this test reduce.c. At this point of time, very strangely, the empty file is put here because empty file is actually the buggy input for this program, because it is just raising an exception instead of doing anything meaningful here. So now let's do this. Let's write nothing and just return here. And we in the spirit of test-driven development, it is a perfectful patch for the bug we just found. The bug we found is the empty file, and this is the perfect solution for the bug. So okay, let's assume we are good. And we fuzz again, and we are going to run the fuzzer. Fuzzer is basically randomly generating the input file and see if the input file, the randomly generated input files are good for your solution. And it is going to find another buggy program that is also very big. Now this is 3,300 lines of code. And again, we're going to reduce again. At this time, it is going to take a little bit longer because it is trying various ways of reducing this file. The reducing to the empty file, which is very obvious, doesn't work for our patch for now. So it is going to randomly finding the more smaller inputs, smaller bug input for your compiler, somewhat intelligently. In other words, it is parallelizing. It is generating a lot of programs in parallel and see if any one of them is still buggy for your program. Oh, it just finished the reducing the input program. Let's see how it looks like. Oh, this is just a single variable declaration of type integer that has anonymous name. So this is the another buggy input for your program here. So you need to deal with this input later. So in this way, it is going to find this fuzzer is going to find the buggy program for your solution for homework 1 through 7 or 8. So that it is going to help you in developing your homework. And now let's turn to homework 2, which is IRGen, which is you need to implement IRGen slash mod.rs, and here it is going to translate translation the given CAST, and it is going to translate it into on IR. So this is basically translating CAST into IRAST. And this is a solution, basically. It is just raising every time, but it is a solution. And we can safely run the fuzzer. So I is for shorthand notation for IRGen. So at the first iteration, it just found the buggy input because we just gave a very naive implementation of this IRGen. And let's see how it looks like. This is again 3,300 lines of code. That's good. And this is impossible to look into because it's too big. So we are going to reduce it. Again, this is randomly generating smaller files and see if the smaller files are still buggy for your homework. It takes some time, but I'm quite sure it will generate the empty file, because even for the empty file, this code will raise exception. On the other hand, the right solution should generate a valid IR. So let's wait for this to finish, and let's try to implement a high-level architecture of this homework. So it is going to be given a translation unit, which is defined in IR, which is residing here, translation unit. So it is going to be given a decals. So as we discussed in the previous lecture, we are going to iterate through the translation unit. So unit.decals. We are going to have a for loop. For all declarations in the translation unit declaration, we are going to do something. So that is basically something we need to do. And in the meantime, let's see what happens. Oh, it is not yet finished. So this is burning my CPUs. Okay. Let's wait for it to go. Okay. So for each declaration, we are going to inspect the declaration, and if it is maybe we should have a name and declaration, and if it is a variable, initializer, do something, and if it is a function, also do something. So this is basically the code we're going to implement here. So we need to this translation unit is a CAST, not an IRAST. So I looked for a wrong file. So I actually need to see I actually need to see the CAST's translation unit. So I need to look for a documentation which can be generated by this cargo doc, and it is just documenting everything that is depended by this KAIST compiler, and it is going to open a web browser. So if you are working on a server, the cargo.doc open doesn't open your web browser, but cargo.doc creates the folder that is containing the documentation. So you can copy and paste this doc folder into your local, and then open them in the browser to see what's going on there. So okay, it is almost finished opening the KCC doc, and we are going to look for a declaration, actually a C declaration. And here a C declaration is consisting of two things. One is specifiers and declarators. Before declaration, we need to look for a translation unit in the CAST. It is consisting of a vector of external declarations. So we need to iterate through just here. And because this is a node, we need to look into the inner definition of this. So this node becomes these external declarations. So looking at external declaration, it is consisting of three cases: declaration, static assertion, and function definition. So we need to deal with each of them. So function definition. How it looks like. One def. Static assert. Probably static assertion is not dealt with here, so that's supported. We don't need to support it. Okay, so translation unit is has a vector here, so we are going to iterate through 0 like this. Okay, blah blah. So this is basically how you approach to the homework. You first look into the type of the type of the argument, and you're going to split it and deal with each of them. So for now, this is not returning it correctly, but let's say at the end of the day, we are going to return just this, and it is going to compile. And after that, maybe we can do register again. So in the meantime, the register finished its job. So it generated a smaller file that is like this. This is just a single declaration file that is only containing the main function returning void. So this is the buggy program for your original solution for this translation. And this is going to, if you manage to if you change this definition and you manage to get this input file to get right, then it is going to give you another error program, and you're going to deal with this in later steps. So by doing so in an iterative way, so by repeatedly fuzzing your input, your program, your solution, and deal with such a buggy program, you will finally produce the right answer that is answering correctly for all the programs that is randomly generated by this fuzzer. So after that, you can submit your solution to the gg.kaist.kr so that you can check that you actually did your homework.